Nearly 15 billion miles from Earth, farther from home than any human-made object has ever traveled, a single aging spacecraft passed through a region of space that, according to every model built to describe it, should not have been there at all. Temperatures reaching tens of thousands of degrees, a boundary behaving nothing like the calm, gradual transition scientists had spent decades predicting. And at the center of it, a discovery about magnetism that quietly rewrote how we think about the connection between our solar system and the rest of the galaxy. The spacecraft is Voyager 1. It is completely alone out there, farther from any other functioning instrument than anything in the history of exploration, with no backup, no repair option, and no second machine anywhere nearby to confirm what it's seeing in real time. Launched in 1977 on a mission originally expected to last about 5 years, it has instead spent nearly half a century proving again and again that the edge of what we think we understand keeps moving the moment we actually go and check. And what it found at the true edge of our solar system is stranger and more important than most people realize. Tonight, we're breaking down exactly what Voyager 1 detected at that boundary, why scientists nicknamed it a wall of fire, and why it isn't dangerous, even though the numbers involved sound like they should be. Let's start with where this boundary actually is, and why it matters. Our sun doesn't just sit quietly in the sky providing light and heat. It constantly releases a steady stream of charged particles called the solar wind, blowing outward in every direction at extraordinary speed, sometimes over 1 million miles an hour. That wind inflates a vast invisible bubble around our entire solar system called the heliosphere. Every planet, every moon, every spacecraft we've ever launched exists inside that bubble, shielded by it without most of us ever thinking about it. Its outer edge, the point where the pressure of the solar wind finally gives way to the pressure of the interstellar medium pressing in from outside, is called the heliopause. It's the actual physical boundary between our solar system and the space between the stars, not a metaphorical line on a diagram, but a real measurable transition somewhere out past the orbit of every planet we know. Voyager 1 crossed that boundary in August 2012, becoming the first human-made object in history to leave the solar system entirely. Voyager 2 followed in November 2018, crossing at a different location and a different distance from the Sun, since the heliopause isn't a fixed sphere. It expands and contracts as the Sun's activity rises, and falls over an 11-year cycle, meaning the two spacecraft encountered it under different conditions, at different points along its shifting edge, which is itself part of why comparing their data has proven so valuable. For decades before either spacecraft got there, the standard scientific expectation was that this boundary would be a smooth, gradual handoff. Solar wind particles slowly thinning out on one side, interstellar particles slowly increasing on the other. A calm blending zone, not unlike the way a river gradually mixes into the sea. Nothing dramatic, nothing violent. That is not what either spacecraft found. As Voyager 1 and Voyager 2 crossed the heliopause, their instruments recorded something researchers ended up nicknaming a wall of fire. Both spacecraft measured particle temperatures in that boundary region, reaching somewhere between 30,000 and 50,000 Kelvin, roughly 54,000 to 90,000 degrees Fahrenheit. For comparison, that's hotter than the surface of many stars and considerably hotter than the surface of our own sun. And it was happening not inside a sun, not inside any star at all, but at the outer edge of our own solar system, in a region models had predicted would be cold, sparse, and largely uneventful. Instead of a smooth, gradual fade from one environment to the next, both spacecraft recorded abrupt shifts in particle density and magnetic field strength, almost like stepping across a genuine threshold rather than drifting through a gentle transition zone. Here's the part that makes the name misleading in the best possible way. This wasn't fire in any conventional sense, and it wasn't dangerous to either spacecraft. The particles in that region genuinely were moving at extremely high energies, which is what gives them that staggering temperature reading. But temperature, in a region this empty, doesn't work the way it does down here on Earth. Heat only transfers efficiently when particles are packed closely enough to collide with each other constantly, the way air molecules do in a room, or the way molecules do in an open flame. Out at the heliopause, the particles are spread so thin that meaningful collisions are rare. Individual particles carry enormous energy, but there simply aren't enough of them bumping into each other or into a spacecraft passing through to transfer that heat in any way that could cause damage. It's the difference between standing in a crowded room where everyone is shouting at once versus standing in an empty stadium where only a handful of people, scattered far apart, are shouting just as loudly. The energy per particle is identical. The overall effect on anything passing through is completely different. Both Voyagers passed through completely unharmed, still functioning, still transmitting, on the other side. So the wall of fire is real, in the sense that the particle energies are real and the temperature measurement is real, but it behaves nothing like fire as anyone standing on Earth would understand it. It's less a wall of flame and more a wall of extraordinarily energetic, extraordinarily sparse particles, violent in principle, harmless in practice. But temperature wasn't the only surprise waiting at that boundary. The second discovery is, in some ways, even more significant. For years, scientists assumed that crossing the heliopause would mean crossing into a completely different magnetic environment. Inside the bubble, space is shaped by the sun's magnetic field, carried outward by the solar wind. Outside the bubble, space should be governed by the separate, unrelated magnetic field of the wider galaxy. Two distinct magnetic personalities, cleanly divided at the boundary between them, the way you might expect two entirely separate weather systems to meet without truly mixing. Instead, both Voyager spacecraft found that the magnetic field direction on either side of the heliopause was strikingly similar, in some measurements running nearly parallel rather than sharply diverging the way theory had predicted. That similarity turns out to be the direct result of the same wall of fire phenomenon. As the sun's magnetic field lines get carried outward and compressed at the boundary by the solar wind, they interact with the galaxy's magnetic field through a process called magnetic reconnection, where field lines from two different sources effectively snap, rearrange, and release stored energy in the process. That released energy is what's accelerating particles to such extreme temperatures in the first place. Space physicist Amy Chen, discussing the phenomenon in a 2024 lecture at NASA's Jet Propulsion Laboratory, explained that this magnetic reconnection process converts kinetic energy directly into particle acceleration and heat, which is exactly why the boundary runs so much hotter than anyone predicted. Put simply, our solar system's magnetic field and the galaxy's magnetic field aren't cleanly separated at all. They're linked, actively exchanging energy at the boundary between them, in a process that had never been directly measured before either Voyager physically passed through it. It's a genuinely different picture of where our solar system ends and the galaxy begins than the one scientists worked with for decades. This matters for a reason that goes well beyond academic curiosity. The heliosphere isn't just a boundary line on a diagram. It's a shield, deflecting a significant portion of the highest energy cosmic radiation drifting through the galaxy before it ever reaches the inner solar system, including Earth. If the interaction between that shield and the surrounding galactic environment is more dynamic, more energetic, and more directly connected than any model assumed, that changes the starting point for understanding how stable that protection has been and how it might behave over very long timescales. It's not a small correction to a textbook diagram. It's a genuine update to how scientists think about the physical relationship between our solar system and everything beyond it. There's also a practical reason this discovery took so long to arrive. Every model of the heliopause built before either Voyager reached it had been constructed entirely from a distance, using telescopes, theoretical physics, and educated extrapolation, but never a direct in-place measurement. That's a bit like trying to describe the weather on the far side of a mountain range, using only equations, without anyone ever actually walking over the ridge to check. Voyager 1 and Voyager 2 are the only two instruments in history to actually make that walk. And what they found, once they got there, didn't match the extrapolation at all. And here's what makes this discovery even more remarkable. It could only ever have been made by an instrument physically sitting inside that boundary as it happened. No telescope on Earth, no satellite in Earth orbit, no probe. Anywhere else in the solar system could have measured this. Every previous model of the heliopause was built entirely from the outside, using theory, mathematics, and remote observation. Voyager 1 and Voyager 2 remain the only two direct, in-place corrections humanity has ever been able to apply to those models, because they are the only two objects that have ever actually been there. And because they crossed the boundary at different times and different locations, comparing their readings gave scientists something even more valuable than a single measurement. Confirmation that the wall of fire wasn't a one-time fluke unique to one spacecraft's path, but a genuine, repeatable feature of the boundary itself. Voyager 1 is still out there right now, continuing to move deeper into interstellar space, entirely alone, at a distance where a radio signal takes roughly 22 hours to travel one way. Its power supply, drawn from decaying plutonium in its onboard generators, shrinks by about 4 watts every year, and NASA's engineering team has spent years carefully deciding which instruments to shut down permanently in order to keep the spacecraft transmitting for as long as possible. In November 2026, it's set to cross a distance of 1 light day from Earth, roughly 16 billion miles, becoming the first human-made object ever to reach that distance while still alive and still sending data home. Every one of those milestones matters because Voyager 1's remaining instruments are still capable of measuring exactly this kind of unexpected structure in the space it's currently crossing, wherever that turns out to be next. As long as it keeps transmitting, it remains the only direct witness humanity has ever had to what actually happens at the edge of our own solar system, a boundary, That turned out to be nothing like the quiet, uneventful line on a map that scientists spent decades assuming it would be. So the next time someone describes interstellar space as empty, cold, and uneventful, remember what a single, aging, nearly 50-year-old spacecraft actually found waiting there. A wall of energy hot enough to rival a star's surface, entirely harmless because of how sparse it is. A hidden connection between our sun's magnetic field and the magnetic field of the galaxy itself, discovered only because something was finally there to measure it directly. Voyager 1 is alone out there, farther from any help or backup than anything we've ever built, with no other spacecraft anywhere nearby, no repair mission possible, and no way to ask for a second opinion. And even completely alone, it's still finding things nobody expected to exist, using instruments designed decades before anyone knew exactly what they'd eventually be asked to measure. If you want to know what Voyager 1 finds next, out at the true edge of everything we call home, subscribe and turn on notifications, because as long as it keeps transmitting, this channel will keep telling you exactly what it hears.